Now, let's have a look at trying to solve some problem using the Fourier transform. So our problem is the linearized KdV, which is the KdV, not a very exciting equation, the KdV minus the nonlinear bit. So, how do we solve this equation? So we have some initial condition. And this is ideally suited to it. The x goes from minus infinity to infinity. There's no boundary condition here. If we have boundary conditions, then we want to bring in the Laplace transform. So, or some other versions of this Fourier transform. So we take the Fourier transform of both sides. Of this equation, of equation 1. So we get the time derivative just does nothing, and the x derivative becomes multiplication by ik. So we've got a qubit multiplied by u hat equals 0. And now I cubed is minus I, so we've got the time derivative of u hat, and this is, we've removed the derivative. This depends, u hat is a function of, we replace the x variable, it's a function of k and t. So it has this function of so it's a function of k now instead of x. Okay, so it's minus I k cubed u hat equals 0. So we can solve this here and just go, well, u hat must be equal to some constant that depends on k, obviously, multiplied by e to the minus I k cubed t, sorry, plus I k cubed t. Okay, and we take it over to the side. So there's the solution to this equation, right? The time derivative is, and then we can find a from the initial conditions. So the initial condition is u hat, u at of x comma 0 equals f of x. So the Fourier transform at a function of k comma 0 is going to be f hat of k, Fourier transform of the initial condition. So finally, we get our solution here. U hat must be equal to the Fourier transform of the initial condition multiplied by e to the I k cubed t. So what we've got, this is, now it's sort of formal, and then we can write down the inverse Fourier transform and work it all out, right? But what we've got access to is this thing called the fast Fourier transform. So at the moment, we've got this solution here. We can write it down using the formula of inverse Fourier transform. Oops. So there's the formula there. But it's not, this formula is not a heck of a lot of use, and we're not going to be able to evaluate this integral. What we've got is this amazing thing called the fast Fourier transform, which essentially allows us to take a function, Fourier transform it, then we can multiply by either the ik cubed and inverse Fourier transform, and all that can be done really quickly. So now we're going to talk about the, I'm going to talk a little bit about the fast Fourier transform. Okay, so now we're going to start, we're just going to learn how the Fourier transform works, and we're not going to get into why, and we're just going to show you, and then we'll talk about the whys later. And we're just going to actually just get it going in practice. So we take xn just to be a sequence of points that are evenly spaced. Doesn't really matter where they start, as long as they're evenly spaced. That's x naught, okay, and this is xn minus 1. So xn is equal to the starting place plus this delta x times n, and n goes from 0 to n minus 1. Now, so that's the discrete point. So we're going to have f of x. We're going to approximate by some vector f of xn. right? We're going to take the value of our function and evaluate it at those discrete points. Now, when we go to the Fourier space, we've got to work out the values of Kn. Now, one of the things about the Fourier transform is that it doesn't really operate on a line, it operates around a circle. Okay, it's much easier better to think about it as a sequence of points around the circle like that. So, and that will explain to you, these are the values of K. So the values for Kn, when you use this is all about the fast Fourier transform, okay? The values for Kn are ordered in this very weird way. They're equal to n times delta K, for 0 goes n to n over 2. Okay, because this is 1 up to here, this is the one over here is n over 2. Right, we've gone halfway round. And then the back half of them, numbers, it starts to count down, and they've got to be done negative. They're not positive. They're actually these ones, but they're from negative, counting down. So they're n minus n delta K and we've assumed here that n is even. When we do this fast Fourier transform, we always want n to be divisible by a multiple of we want it to be a power of 2, so it's to get the full advantage of the algorithm. It speeds up much. It runs as quickly as it can if the number of points is divisible with the power of 2. So it's like if it's 4, 8, 16, 32, 124, that kind of thing. But you get the idea here that the counting, the reason the K appears to count in this very strange way is because we go up here to here, and then we start counting back from minus. So we finally end up here coming down to a negative. So these are negative numbers. The second half here, these ones are all negative. So this is just a formula that gives you the K. If you don't do this right, the Fourier transform, you won't multiply by the right K in Fourier space. And the delta K is equal to 2 pi divided by n divided by delta x. So delta K times delta x is equal to 2 pi over n. And that's a discrete version of Heisenberg's uncertainty principle, which says that change in momentum is a constant here. The accuracy, the momentum to the accuracy, the space, and it's all about aliasing and things like that. This is a really important idea. So as you refine the delta x, you also refine the delta k. Okay, the number here, I should say. All right, but that's the formula here for delta k. This is all just a formula. You just set x up, and you can go from start somewhere, but they've got to be evenly spaced. So you have a constant delta x. So that's your x naughts. And then where the delta k doesn't care at all about where you start, it just goes all the way around the circle. But it does depend on your delta. It depends on the delta x and the number of points through this delta k. Okay, but it's just a few lines of MATLAB code that you punch in. Okay, so this is the code here. This is the code fragment from the that's in the notes. I'll just put it into MATLAB. I'm just going to quickly change the font. So let's just see how simple this is to do it. So we take n to be 1024, okay, 2 to the power of something, 2 to the power of 10. And we have our x going from minus 10 to 10. So, and we have n points, evenly spaced. This just sets up an even spacing between minus 10 and 1024 points. And that's the delta x and the delta k given by my formula here. Delta x is just the spacing between each point, so I might as well take the second minus the first. And then the k is this funny formula here. So it goes up and then counts down. That's just written in compact notation, counting up around the first half of the circle and then back down. And then here's my initial condition here, f of x is equal to e to the minus x squared. So now I want to calculate the solution at some time later. All I do is I Fourier transform f, and then I multiply that Fourier transform by e to the ik cubed times t, and then I inverse Fourier transform Okay, and then finally I put this real part here, but that's just to get rid of any spurious, because the fast Fourier transform is very much about complex numbers. So it'll produce any little numerical error, it'll produce a tiny imaginary part which can kind of fool the computer. But there it is there, that's as simple as that. So let's just run that. Whoops, I don't want to run it. I'm just going to go Control Enter and have a look at the picture. Okay, it's a brilliant piece of code, but it doesn't do anything. So let's just draw a picture of this. Plot x, comma, f, the initial condition, and x, comma, u, the solution at time t later. All right, let's run that again. And there's the solution here. So that's the initial condition, and then at some time later, you start to see it break up, and then you get these trailing waves coming forward like this. So if we multiplied this by, let's just try and make a little movie here of the solution here. Okay, so we'll go for t equals 0, 0.01 to 1. Okay, I don't know if that's going to work too much. We'll plot the thing in the initial condition, and then we'll get it to pause for 0.01, and then we'll go end. Okay, so this is going to start out, and it's going to plot it, and let's see what happens. Okay, there it is there. Okay, didn't you think, what a neat figure there? Wow, things have gone crazy. Didn't pause for long enough, did we? Okay, well, for 0.1 we need to leave 0.1 to. Alright, so start again. And there's the solution propagating away. Okay, and you can see what happens here. It actually comes back around the circle because it's on the circle. So these waves are coming out of here and coming back in here. So the solution's only valid for a certain amount of time. And we can fix that up. So it's one of the, nothing's perfect in life. It's on a circle. You can see that beautifully. So we could make this, increase the spacing to 100. That would take it longer to come back around, wouldn't it? Let me make sure I've lost my picture of the circle. Try that one. All right, you can have a play around with this though, and you can see how it works. Okay. All right. And there it goes. Okay, so this is going to take, it's not going to get back around the circle. Okay, still, there it is. It's producing this trailing wave. Okay, as it evolves forward. All right, brilliant. So, if we change this to either that, we got rid of the cubed here, then it's interesting to see what happens. Just a bit of play around with it. Not a lot. It's hard to see it. I should have done, I'm going to stop that. I'm going to just change this to be back to 10 here. Let's see what happens, all right? So look at that. Okay, nothing, it just moves, shifts. Okay, because this is the e to the ikx, this is the e to the ikt, that's the shift operator. You multiply by that. Okay, so it's just that is what in Fourier space, remember I said to you that the shift operator becomes multiplication, but not multiplication by ik, multiplication by e to the ik times the amount of the shift. All right. I'm going to finish there. So you can see here how neat and how powerful this is, and you can very simply solve these problems using it with a few lines of code. And of course you can reuse all this code here with the delta.